Good evening, everyone. I hope I'm audible.
Yeah, good evening, sir.
Good evening. All right. So, just to get started, like I will just do a quick recap of what we did in the last session, and then we'll continue from today's one. In the last session, we primarily talked about the process capability, how to check the sigma level of the process, how good or bad is your process. So we have these three ways of checking sigma level or the process capability. One is in terms of percentages, which is what we might end up using too often when we deal with people who are not well versed with the language of sigma levels and all. So yeah, we should be able to explain them the process performance in the language of yield. Uh, for our internal assessments, not for the client, we should be looking at throughput yield and roll throughput yield. Yield is reported to the client, the external client who pays for the product or services. Uh, Coming to the sigma levels, then we'll talk about like various nomenclatures like CP, CPK, PP, PPK, Z bench, and all, which will help us calculate the sigma level. We get the sigma level from this particular these variables. And then we have the last method, which is DPMO method to calculate sigma level. So first thing first, when we talk about yield, it's nothing other than what's the quality of your process. How do you define the quality? How do you calculate the quality of the process? Given the customer requirements, we try to assess the quality of the process. So we like the basic formula. Basically, there was just one single formula, which is why how we calculate it. It's the norm dest formula that we used to calculate the lower side defect, the upper side defect, and once you get both the side defect, you add them up, you get your total defect, and finally you subtract that from one to get your overall productivity, which is the yield of the process. That's how you generally we go ahead and calculate the yield. Now, with the same logic, we also talked about this TPY, which is throughput yield, which is where we look for uh, error-free, like defect-free output of the process, wherein we consider scrap or, for that matter, rework as a bad. So technically, we are just looking at the net output of the process without any error. And when you want to look at, this is at stage level, at process level. So stage one, stage two, stage three, stage four, multiple stages can be there in the process, but my process starts from the beginning, goes till the end. So I will be able to check the individual stage level process output. But when I'm looking at overall productivity, that's when we look at rolled throughput yield. And how do we calculate this? We multiply all the throughput yield to get the rolled throughput yield. This is probably at a manager level, at a like at a stakeholder level. You would be assessing your performance as a super boss. Practically, you would be looking at your own rolled throughput yield, and you'll be giving feedback to your team on the basis of throughput yield. So that's how ideally the process should be evaluated internally, not for the client, but internally. We would like, it's not being more stringent, but it's being realistic. It's being uh, honest to ourselves, because when we calculate yield, we don't look at the number of reworks we do, which is bad. Like client doesn't care. You may rework 100 times. That's not a problem for the client. But yes, for us, that's definitely a problem because you are reworking, you're reutilizing the same resources, you're wasting time, resources, material, practically efforts. So we would like to emphasize on that. And that's how we should start evaluating our process, people, everything. So these two would be the right metric to look at. Coming to the sigma level calculations, we talked about CP, which is the process capability, but we have got two significant drawbacks of CP. Is that like it can't tell you how you're performing; it just tells you the capability, how good you can deliver, but it doesn't tell you how you're delivering. Uh, Secondly, it's not applicable for all process because you have to have both side specifications given by the client to calculate CP, like upper limit and lower limit. That's only when you can calculate CP. The formula needs both of them. So there are a lot of metrics we talked about which just have single side specifications. We talked about some of them like sales. You get lower limit, minimum sales required, minimum quality required. you only get minimum limit. So you can't calculate CP. Time related, cost related, you get maximum limit. Well, you can't get a lower limit for this. So such metrics you can't calculate. Only actually when you make a product, when you have dimensions, that's when you generally get a two-side specification. So all in all, we're interested in knowing how we're performing. For that, CPK comes into picture. So CPK helps you overcome both the drawbacks. One is if you have two-side specification, you can calculate sigma level. If you have upper limit, you can calculate sigma level. If you have lower limit, still you can calculate sigma level. So, and it tells you exactly how you're performing. So we have the formula for upper limit. We have the formula for lower limit. We just need to put in the values. These values will be coming from your process and from the client. So upper limit will be given by the client. Average of the process will be taken divided by 3 standard deviations. So you put in the value, you get your upper limit, upper capability, you get your lower capability using this formula. Minimum of them gets chosen as a CPK. And finally, when you get your CPK, you multiply that CPK with 3. You get your long-term sigma, and you have to manually add 1.5. Keep this in mind, this is a manual addition. You have to add manually 1.5 to get your current sigma level. We only report current sigma level. Whenever people talk about sigma level, they always talk about current sigma level. So keep this in mind. They're always adding 1.5 to the long-term sigma, which comes from the formula, which comes from the process, and you add 1.5 to get your current sigma level. That's the nomenclature, that's the culture which was started by Motorola. So when we say Six Sigma, it's a current sigma. It is same as 4.5 long-term sigma. There's a difference of 1.5. So you add 1.5 to report current sigma of Six Sigma. So that's the culture. Practically, the performance level is same. You're just creating a new variable. That's it. You had a long-term sigma. There's a performance level at this sigma. That's the same level in the language of current sigma. That you say it's a Six Sigma, that is same as 4.5 long term. So and so we talked about basic difference, like when we say Six Sigma process, it is you either say Six Sigma current, or you say 4.5 long term, or you say 3.4 defects in a million opportunity, or you say a quality of 99.99966%. We are talking about same performance level. So all in all, we got to keep in mind the difference between long term and short term will be 1.5. 1.5 current will be higher and the long term will be lesser. By the virtue of law of diminishing returns, everything deteriorates with time. So it will change by the now that's where the question comes into picture. There's no such timeline, and that's why this is a very debatable topic. See, there are a couple of things which can be argued here. One is, what is the timeline? This is a gray area. It says with during the course of time. Now, what's the definition of time? It varies from process to process. Why 1.5? Like, this was not same for every process, like 1.5 sigma level change. Some process had a bigger change, some process has a lesser change. This was average. So finally, this was created by Motorola. Say they fixed it as 1.5. So that there are people who don't consider this as a metric. They just, so again, it's just all we got to keep this in mind, because the culture started from Motorola. Most people practically only report the current. So even if you don't believe this version, practically it's just a extra bit of activity which is added by Motorola. But in reality, the actual sigma level comes from here. We also looked at Z table to look at the Z table, how to read Z table and calculate the number of defects against a particular sigma level. So we will go through the recording. I'm sure it'll be clear. The DPM method was the simplest out of all. You just need to use this formula for calculating DPM, which is norm sin V. And like, so that's the formula, norm sin V, 1 minus whatever is the defect rate. Say we wanted to calculate sigma level for 23% defect. So 23 out of 100 plus 1.5 to make it current. Similarly, say we wanted to know, and just an arbitrary number, like any number, 1047 defects out of some 23,007, whatever this value is. So if what is the sigma level for this process if we have these many defects? Well, same logic. We'll have norms in V1 minus what is the defect out of the total plus 1.5. So basic logic remains the same. Rest the formula will take care of. So this is the simplest out of all of them. All this what we discussed was coming from, like, it was from the Six Sigma, the sigma level calculation. So if we talk about the analyze phase, it has two primary reasons. One, we would like to know what is the sigma level of the process. Second, we would like to perform the statistical test, because that's what we talked about initially. Analyze phase has two reasons. One, we would like to know where do I stand right now? What's my performance level right now? We have not improved anything. It's what we have. Like we will improve, then we'll gauge what's my new sigma, but let me know what's my current sigma. So that's what we calculating the sigma level now. And today we'll be covering about the statistical tests, how to perform this test on various data to understand what's the root cause. The reason why we did Six Sigma project was just because of this reason, that why, like if I'm facing a problem, there are multiple possible reasons, but which one is the real one? That's what we would like to figure out today. That's what we'll be covering up. This is going to be an independent topic, so again, it's no linkage with your prior topic as such, so wouldn't be a problem there. Now, before we move on, there was a question towards the end of the session. What if we get a data which is non-normal? We all talk about the normal data. What if we get a data which is non-normal? So we, like briefly, I just talked about this towards the end of the session, that we have four different ways how we deal with non-normal data. Uh, One, it says if you increase the sample size, there's a, in stats, the theorem is like central limit theorem is there, which basically talks about the normality piece. It explains the normality. So by the virtue of central limit theorem, every data approaches normality. As you increase the sample, it slowly, steadily becomes the population data. It acquires the features of the normal distribution. So just to kind of, if you want to quickly have a look at this, I'll probably be able to demonstrate this for you. Say sample one, just to kind of show it to you how, but this is not something which we do unless and until your organization, your sample collection is not a big deal, and it's not a costly affair. You would not end up increasing the sample for normalizing it, because sample cost is a big concern. But yeah, if your industry is IT driven, everything data is coming from IT driven sources, it may not make a big deal. You might increase the sample. So let me just quickly create some random data just to show you how the data can, so this is like 10 data points. I want to store it under sample. So there's an average of say 25, the standard deviation of say 3. I'm just randomly putting some values, and I'm creating some random data. 10 values. Then we have got, say, I'm creating 100 values. Try to see the shape of the data. And we all know how normal distribution looks like. We'll be able to evaluate what this central limit theorem talks about. Like I'm just increasing the sample size, and trying to, we'll look at the normal distribution for this one. How does the shape changes as we increase the sample size? It acquires the features of the normal distribution. So we've got different sample sizes, like I've kept on increasing it. Let's have a look at it one by one. Let's just have a look at it. So histogram, let's like width fit. This is the normal distribution. I'm just trying to go and pick it up. Let me just pick up all of them at one go. Select. Let's see, it should give me 5 different blocks. Yep, have a look at this sample one. See, the normal distribution doesn't look like a normal distribution. Like the image is there, but the data doesn't look like a normal distribution. You should have like most of the data in the center sort of thing. So it's going out of it. Some data is not present, some data is not present. A lot of data is, less data should be, it should follow the structure. This is the shape of a normal distribution. It's not, it's going out here. It's going out here. You don't have data here. It's what normal distribution doesn't look like this. Let's, if I increase the sample, there was like 10 samples here. If I increase the sample, let's have a look at sample 2. It started getting better. Like it's getting better. Like it's still, the peaks are forming here. It's getting better, but yes, we still have some with 100 values. The shape will keep getting better. Look at this one. Same values. So I did not change the average. The same average and same standard deviation. I did not change it. Let's see, it's acquired a much better shape now. The data is like forming this line sort of shape. And let's have a look at it. This was 1,000. This is say 10,000 samples. Look at this shape. That's how, that's the logic behind it. And look at this, a perfect shape. So if you look at, this is like a real-time demonstration how this rule works. But yeah, and unless and until your organization is in some IT kind of world, where probably IT driven data can be easily obtained without too much of fuss, you can go ahead with this logic also. But generally people don't use it. We go generally with the logic of removing outlier. You can use your box plot kind of rule and you see what kind of data or exceptional values which are kind of making the data non-normal, remove them. But keep this in mind, whenever you remove any outlier value, exceptionally high value, exceptionally low value, then you must do a root cause analysis, use the data for remaining data, but understand why that happens so that you can keep that in mind going forward, why that happens. So you'll be able to kind of safeguard yourself for that. So when bottom line, whenever you mess up with the data, when you change the data, you should know the reason and you should document it somewhere why you did that, because tomorrow you don't want somebody to come back and question the integrity of the process. One. Second, it helps you plan your future action plans, or keeping those factors in mind. It might give you some reasons why you may facing a problem in your process. So this is most common one. Then it talks about some transformation methods. Like transformation methods are good just from research purposes. I would not use this in a real world, because, and I'll probably just show it to you how it works. But transformation means if my data is say non-normal, I'm trying to use some transformation rules and it's changing the data. See, it's no longer my own data then. It's changed. The data is changed. Yeah, from research purposes, people who are into research world, probably doing a PhD in stats and something like that. Yeah, everything started from normality. Everything evolves uh, around normality. So they would translate everything in normality, in normal distribution, and try to see, had this data been normal, then what would have been the situation then. So transformation looks good there from research. In real world, you can't explain this to your management. And let me quickly show you. Having said that, if you use these methods, it doesn't guarantee that it will convert your data as a normal. It will try, but it doesn't guarantee. Still, let's quickly have a look at the sample data. I've just uh, I've got this sample data here. Just copy paste this data. Let me show you how this data looks like currently. Uh, Let me just get rid of this one first. Okay. Okay. So that's the say data, and I'm going to paste this. Let's quickly have a look at the normality for this data. Is this normal, non-normal? It'll give a clear picture. This is non-normal, p-value less than 0.005, less than 0.05. No, that's it's this is highly non-normal. It says less than 0.005. So this is non-normal pretty much. Let's see how we go about these. One is like if you go and if you see this one, there are two tests that we have. One is a Box-Cox transformation, another is Johnson transformation. Johnson is more robust than Box-Cox, but still let's have a look at it. Stats, quality tools, and here if you go to, like, forget, let's look at the Box-Cox first. So chart control charts and says Box-Cox transformation. Okay, let's kind of use this data. I go to option. It's asking where do you want to save it. I want to save it under C2 column. If this data gets transformed, see, it's using some lambda sort of rule to change the data. And if it gets changed, it'll just, let's see whether it's able to store the transformed data where. So I'm saying under C2. Let's see if the data which is transformed, is it normal or not? Let's have a look at it. So the new data has been created from this data, but look at it. Would you be able to explain what this 94 has changed to 9.6? What different values of like this data is altogether different. You can't explain this to your management what this change is all about. But let's see, is it normal, non-normal? So say test. Let's see, is this transformed data normal or not? Still non-normal. As I said, it doesn't guarantee that it will convert the data, the converted data will be a normal data. No, it doesn't guarantee that. It tried, but it could not create a normal data. Let's have a look at Johnson, whether does that solve the problem or not. Let's just clear the cells. Okay, so stats, we've got quality tools, and here we got Johnson transformation here. Johnson transformation. This is more robust. Let's say select data here. Where do you want to store it? Under C2, that's it. If it gets converted, That's only it will store the data. Let's click it. Okay, yeah, it's done. When you get this image, otherwise it would have given you failed. So it's, look at this. Earlier, the image of the data was like this, and some data points here. It was non-normal. Now it's converted, transformed into a different shape. It's falling within a line. Used it has used some transformation function, some sort of transformation function, some sine cos theta. God knows pretty much. Doesn't don't need to know in the SQL. So, but yes, it just transforms the data, and let's have a look at it if it follows the normal distribution. No, but look at this data. Say new sort of thing. It is negative values also, minus 1.47. Well, I can't explain this data to anyone, to my management. So in real world, practical world, practically this would not be applicable, but let's see. Yes, that's converted as a normal data. So non-normal has been converted to normal data by the use of this transformation function. So, but in reality, again, that's what we don't end up using. Yeah, people from research, is it wrong? No, it is not wrong, but it's hard to explain. It would, because the audience that you're dealing with, they are not statisticians. So you can't explain this any which ways to them, and they would not be able to make sense. Your data is not no longer your data. That's how I would put it. So I'll just cross it off. But all in all, we end up using this. And the fourth option is the preferred option. Again, should you know the the black belt part of it. Now, and as a black belt, you end up dealing with other types of data, which is specifically the non-normal data, the categorical data, when you end up using basically the non-parametric test. Parametric test means normal data, the normal data related test. Non-parametric is non-normal test. So there are tests for non-normal data. So they don't change the data, let it be non-normal. They'll use the data as non-normal test, and they will have certain tests for data the way it is. So if it's normal, they'll whatever test we will be covering, we'll be using that. But if it's non-normal, they will have a separate series of tests which we will be used for non-normal data. So there are different approaches of like dealing with the non-normal data. So again, practically, you can use whatever you're comfortable with. In a practical world, this is not in use, but rest of it definitely can be practiced. I hope you're good with this, everyone. Okay. Right. So, all right. So in today's session, we shall go ahead and get into the statistical part of it. Now, the statistics is what we're going to be dealing here. So first thing first, we will be looking at hypothesis testing. So hypothesis, what do we mean by hypothesis testing is what we will like to understand, because before getting into the test, we again still need to go through some bit of little bit of theory so that we understand the interpretation of the test. Doing it on MINITAB will be few clicks. That's it. It's very easy. But yeah, getting the concept is more important. So basic literal meaning, if you pick up a dictionary, find the meaning of hypothesis, that means assumption. That's what you will see in every dictionary. You'll assumption. You make hypothesis, that means you're assuming things. In stats, there are two types of hypothesis. One is null hypothesis, and other one is alternative hypothesis. Null hypothesis is denoted with a H and a small zero at the bottom, and not just next to it. Well, let me just have the slides in here so that I'll probably be able to show you how does it look like. But in the meantime, we're going to go through this. Let's quickly, let me show you. The symbols should be clear so that whenever we come across H naught, that's how null hypothesis H and a small zero at the bottom of it. So that's null hypothesis, and alternative hypothesis is H small a at the bottom. So that's how we will be, which when you see the symbols, you should know which we talking about null or we talking about alternative hypothesis. Well, some American authors use H1 also, it's sub 1. Instead of A, they will use 1 also for alternative hypothesis. So it's the same stuff. Subscript, thanks. Yeah, that will be the right way. Subscript 0. Yeah, going back to what is the basic difference or interpretation of null. If we go back to the statistical way of kind of interpreting null or alternative, that will become too complex. But yes, try to let me just write down certain basic definitions with respect to null or an alternative, and then we'll then try to kind of introspect everything that I'm writing here. So first thing first, null is a default hypothesis. It's a default hypothesis. It's a current, not what you can say, current knowledge, whatever we know, it's all null. Like we'll try to, I'll explain everything, whatever I'm writing here. Uh, it's a universal truth, hence need not be proven again. If you talk about null, it always states that there is no relation between x and y. Nothing is correlated. Bottom line, you have collected some data. You're talking about like you've had possible causes. You had a long list of possible causes. This could be possible reason, that could be possible reason. But as per null, there is nothing which is correlated.
Kailangan tanggalin plus
There
2.
is there is no relation between x and y. So you had a business problem. You had a long list of possible reasons. Like if you go back here and we look at the data we had collected for this ticket closure time, we had like long list. We had the IT ticket closure time, we had a lot of X's. As per null, this is all junk. Nothing is related in this. In universally practically, there's no relation between X and Y. Nothing is correlated. There's nothing which is impacting your business problem. That's what null is. Null talks about indifference. This is all about indifference. There's no impact, no relation. That's what it talks about. Secondly, if you want to further drill down, say if I'm comparing, like you have two shifts. You have a morning shift and you have a evening shift in your, and you want to compare the productivity of your morning shift versus evening shift. Well, probably you feel that morning shift people are more productive and night shift people probably are very like less productive because they feel sleepy, they're lazy, whatever. Maybe the reason, probably you want to prove that morning is more productive. Well, null will contradict there. Well, null means uh, null when we compare two or more groups. So you may be talking about, you may be having 3-day shifts like morning, evening, and night. So or you just have a morning and evening, or morning or night. So either you're comparing two groups, like I may be looking at male or female, productivity of male and productivity of females. Well, I might say, well, males are better. Somebody might say, no, females are better. Well, so we're trying to compare the productivity of two different groups. We probably, if we have 5 managers, I'm trying to prove that, say, these 2 managers are great, others are not good. Well, I'm trying to compare different groups. So bottom line, what we're trying to do is we're comparing the performances. We're trying to assess who's better, who's lesser, sort of thing. When we compare 2 or more
Doon ka na
groups,
ba?
as per null,
Doon ka na?
every every group is same. There is no difference.
Magkano yung ulam?
So that's what it means
Also,
when we talk about null and all null definition. Technically, that's what it means. If you're comparing, say, male and female productivity, well, as per that, male and female both are same. There is no difference in the productivity of male and female. They have similar performance. If you talk about, say, you have 5 managers, you're comparing the productivity of 5 managers. Well, it says all the managers are same. There's no difference in them. So null will always talk about indifference. It will say no relation, X and Y. It'll say that the people, the groups that you're comparing, there is no difference between them. They're all same. That's what null will all talk about. This is a default understanding. This is default hypothesis, which is what we use with null. Now, to understand this better, like one more thing, like null always comes with equal to, so basically status quo sign. Null will always talk about equal to something. So it this, because it's always says everything is same, so it always comes with equal to sort of thing. Let me give you some example and we'll be able to make sense out of this. Whatever we've written, we'll come back and kind of try to understand with those examples. Say I'm a fond of like chocolates and I love eating chocolate. So I buy the most, like one of the best brands in the market, and I pick up the packet, and on the pack it's reprinted 500 grams. Well, I know it's 500 grams. I believe it's 500 grams. Well, why? Because the source is so reliable. That's one of the best finest, say, Belgium chocolate that I'm using, and I trust it. I'm not going to weigh that chocolate packet. And when I look at 500 grams, I believe it's 500. Even without testing, I believe that. That's printed and it's understood. It's 500 grams packet. When I pick a 1 kilogram packet, I know it's 1 kilogram. I'm not contradicting, I'm not questioning the integrity like this packet. When I look at 1 kilogram, I believe it is that. For example, say we have these car makers like Audi or Ferrari or whatever, this BMW. These say you start seeing the advertisement in the market and in the televisions or various sources that the new car variant will give you 50 kilometers per liter average. Well, that's insane. Well, to car to give you that kind of average. Well, but then I start we start believing it. Why? Because it's coming from a very reliable source. It becomes a current knowledge. We start talking to people, there is a new car which is coming, that's like that's giving 50 kilometers sort of average. So I'm saying car has an average of 50 kilometers per liter. It's always coming with equal to. We are That status quo symbol. So practically we're talking about the chocolate, the weight of the packet is 500 grams. The car has a mileage of 50 kilometers per liter. It always comes with equal to. Keep this in mind. Null will always talk about equal to. Basic meaning of null is zero. Null, nothing. So well, probably one of the easier way to understand this. We all believe in good, that like we our deeds should be good. We should do good stuff. We should not like trouble people. We should do the good stuff. Why? Because see, when somebody dies, you do good stuff and you go up there in the sky. So probably there's a up there in the sky, there is heaven. Or similarly, if you do bad stuff, then you go to hell. So bottom line, we're talking about, have you seen it? No one has seen hell or heaven, but we talk about it. We believe it. Somewhere there is a fairyland. Well, we haven't seen it, but do we talk about it? Yes, it's universal truth. People talk about it. It's a part of a society. It's part of a culture. We talk about all this stuff. It's proven. You don't need to prove this. People talk about this. It's a part of a culture. It's like going on since ages. These are default understandings. It's standard. This is not questionable. These are already there. It's a universal truth, and hence you don't need to prove null. Null is already proven. These are already default. When you look at the pack, it's 500 grams. It's proven. The car, but like Audi, well, I'm sure they must have done some technological changes. Well, that's why it's like 50 kilometers. Well, I start believing it. These are basic like sentiments which are there, like we should do good stuff. Null will always talk about equal to. Now that's where, if we look at alternative, probably the understanding will get sort of better with this null. This is probably our generation, probably our kind of generation, which we were going to question everything. I'm not going to believe because you say so. So this is more of claim. We call it challenge, or you say research. What are we talking about? Research hypothesis. I'm going to contradict. I'll say, no, null, you're wrong. Bottom line, I need proof. I'm not going to believe because you say that this is chocolate packets like 500 grams or car is like 50 kilometers, is going to give me 50 kilometers per liter average. Well, prove me. So bottom line, alternate is all about claiming something. It's all about challenging and saying that null, you're wrong. So alternate will generally, when you look at alternate can come in three different forms. Say I might try to prove, I'm contradicting, I'm challenging that the packet that I've picked up, that pack of chocolate is less than 500 grams. I might try to prove, no, I think it's a little heavier. I might try to prove, no, it's more than 500 grams. Or I might just say, no, it's not equal to 500 grams. All these three statements, I'm contradicting, I'm saying, no, null, you're wrong. Null always comes with equal to. Alternate can come in three different forms. I might try to say it's less than, it's greater than, or I might try to prove alternate. Well, like by saying, no, it's not equal to. It may be more, it may be less, but simply it's not equal to. So all these three versions, I'm saying that null, you're wrong. Now keep this in mind. You don't need to prove null. Null is an existing truth. People believe it, it's already there. Who has got a problem? You've got a problem. You are the one who's coming and claiming something. If you are claiming something, you prove it, not my problem. I'm already proven. Null, I'm already proven. You've got a problem, so you always need to prove alternate. You never prove null. Null is already proven. You need to prove alternate. Well, you may be successful in proving that alternate is right and null is wrong, or you may fail. So keep this in mind. That's what, from technical perspective, from a recruiter's perspective, in a job interview perspective, you got to keep basic fundamental in mind. Recruiters do ask this question. They try to frame people in making this technical error when you kind of commit, when you explain this. Keep this in mind. Because null is already proven, it's a universal truth. You come and challenge that null, you're wrong. So you always try to prove, you have to prove alternate. You are the one who, the burden of proving something is on you, because you are the one who is claiming something. So you have to submit the evidence, you have to prove it that no alternate is right. So what can be an outcome of any proof, like anything like null or alternate, whenever this argument happens? What will be the outcome? A, you will, so keep, this is the basic first stuff. Either you will reject, so basically reject null and accept alternate. So we reject null and accept alternate when we are able to prove, now we have enough evidence, sufficient evidence, that null is right, and alternate is right, and null is wrong. So we will reject null, we'll say no, null, you're wrong, and we accept the alternate. That can be the case when you are able to prove that null is wrong. The other way is where be things can go wrong. The way we put it, we failed to reject null. That's what we have to. We can never, that the only thing you got to keep in mind, never mention null was proven. Bottom line, you can't prove null. So A, you will be able to either reject the null, that means null is wrong, or you will fail to reject it. You cannot prove it. You wanted to prove it wrong, but you failed to reject null. You do not have enough evidence to prove that null is wrong. So you will have either, but this is the only thing you got to keep. You can use and this in any different ways. You can use your own ways of interpretation or how you want to explain this, but never mention that null was proven right. Never. You were trying to prove null is wrong. Either you will be successful or you will fail. That's the only outcome which can happen. Either you'll succeed in proving null as wrong, or you'll fail in proving null as wrong. That's what you got to keep in mind. Like, you can use your own ways of explaining this. Avoid this. That's it. So you might like, so we generally use various statements. These are basic statements that we use for proof, as a conclusion. Or we also use these statements also. We have enough evidence or statistical evidence to reject null and accept alternate. That's sort of a statement like we can use. Or we do not have enough statistical evidence to reject null. You'll not say we proved null was proven right. No, that's, so you can use, you can write it the way you want. Just keep this in mind. Now that's how we figure out what is null and what is alternate. Basic definition. So I might try to prove it's less, it's more. So how do I check it? I might get a weighing scale. I'll try to go and check it out on that. It's more, less. When the testing will happen, I'll get to know whether it's more or less, or whether null is right or alternate is right. I'll get to know, understand that. But basic definition, is it clear to everyone, like how, what is basic interpretation of null and alternate? I will look at some example, but just want to be sure like we've got this correct. Is everyone okay with basic definition of null and alternate? Okay.
Yes.
Okay, let me just quickly show it to you, like, so that we can have a basic understanding. So have a look at the statements. This is null statement, this is alternate. As a result of employee safety program, there will be no difference in employee injury. That's my null statement. Alternate says, as a result of employee safety program, there will be a difference in employee injury. Now, a basic question that can come out to a mind, why can't this be an alternate statement? Why can't this be a null statement? Keep this, again, always keep this in mind. Whenever in dilemma, ask a question from yourself. What are you trying to prove? If you're trying to prove something, that's alternate, because you always need to prove alternate. What are we trying to do here? We're trying to probably convince the management, like probably there are a lot of accidents happening at workplace, and we're trying to convince the management that we must conduct some sort of employee safety program. If we do this, there'll be lesser injuries. We're trying to develop a relationship, X and Y. We're trying to say that no, these two things are correlated. If we do this program, people will be more aware and then will be lesser injuries. Well, null says forget about it. Well, one is a training program, another is injury. Why are you correlating? They're two different things. There's no relation between them. Null will always talk about no relation. Alternate will try to develop a relationship. Like, let's have a look at this one also. This is just, this is again, there's nothing called H2 because there are two versions. We can have less than, more than sort of thing. They've used H2. But bottom line, let's look at the example. Say somebody has a problem of domestic violence, and so we're trying to convince the family that you must take this person for some anger management therapy, some psychiatric treatment. Why? Because if the person goes through psychiatric treatment or some sort of anger management therapy, this person will do less of domestic violence, will be able to control it. So we're trying to develop a relationship between this anger management therapy and domestic violence. Null says forget about it. This is one therapy and this is violence. Why are you kind of correlating them? There's no relation. Null will always talk about no relation. Similarly, have a look at this. Violent video games have no impact on future acts of violence. Null says no. Playing while violent video games will lead to like such acts in the future. So null, bottom line, null will say no relation, alternate will develop a relationship that yes, there is one. But now uh, assuming that you have got it right, I have a very, very simple question, and definitely we would like to kind of get some answers there. Uh, say there is so there is a crime site and somebody is caught by the police red-handed at the crime site. So police has caught the person with the weapon. There is CCTV footage also, and there are a lot of people who have seen the person committing the crime. So there are a lot of witness also. So one, we have witness. Two, we have CCTV footage. We Third, we have got the weapon, and the police caught the person red-handed at the crime site. Now, keeping all these factors in mind, when the person is taken to the court, in the eyes of court, what's the null definition? What's the default definition? Is the person innocent or is the person a criminal? In the eyes of court, in the eyes of judge, is this person innocent or is this person criminal? What's the null definition? Gotham says innocent. How about others? Innocent. Okay, criminal, innocent. Okay, the answer is innocent. And the reason why it's innocent, why? Because just keep this in mind. What are we trying to prove here? If you're trying to prove something, that's an alternate. You don't need to prove null. The reason why you're having a court trial, because you have to prove that this person has committed a crime. You have to have, yes, thanks, everyone, innocent until proven guilty. This person in the court has no liability of speaking even a single word to say that I am innocent. No, you are the one who's got a problem, right? You're the one who's coming and telling that now this person is a criminal, he has committed a crime, show me the evidence. This person is innocent as the judge himself. This person has no liability to prove himself that he's innocent. No, he is innocent. You are the one who's claiming that this person has committed a crime. Show the CCTV footage, get the witnesses, get everything. When you bring the evidence, the judge will evaluate the evidence. Now, in the light of evidence, now we can say, now we have enough evidence to claim them, to prove. Now it's been proven that this person has committed a crime. So we reject null and we accept alternate. Now this person is guilty. The reason why we're having a court trial, because we want to prove that this person has committed the crime. Because we're trying to prove that, that's alternate. The null will be innocent. Whenever in dilemma, that's what you got to do, is simply ask a question from yourself. What am I trying to prove here? The answer will be available to you. So with that being said, that was the core trial sort of thing. What happens in a real world scenario when we're dealing with statistical tests, when we're dealing with data, real business problems? We have some data like this, which is collected. I'm trying to prove that null says this ticket handler has no impact on the ticket closure time. Well, we collected this data because we believed it. There is an impact. Who is handling the ticket will definitely impact the ticket closure time. We want to prove it. Null says no, ticket handler has no relation. Well, probably somebody felt that gender wise there will be impact, male or female. Somebody feels that males are better, somebody feels females are better. Well, We try to prove a point that gender has a role to play. Well, null says forget about it. Null says male, female, both are same. Somebody says age group could be a big root cause. We try to prove that. Well, null says no, doesn't matter. What whether you're young, you're middle aged, or probably you're old, doesn't matter. You all are same. Null will say no relation, everything is same. Alternate will always try to prove a point. No, there is a relation and there is a difference in the performance level. So all in all, how do I know whether null is right or alternate is right? Like when we're dealing with data in the court, we had the evidences, the statistical, the evidences like the weapon, the witness, and all that. In our world, when we deal with data, the evidence is this p-value. We have already been introduced to p-value when we did the test, when we did the normality test. We saw the p-value there. P-value is the evidence which will help us understand, is null correct, or are you going to go with alternate? Are you going to reject the null and accept the alternate, or you will fail? So bottom line, the evidence will come from the p-value. P-value is the deciding factor which will help us understand whether we will go with null or will go with alternate, whether there is a relationship or there is no relationship, whether it's a root cause or not a root cause. How will I find a p-value? But before we get deeper into the p-value part of it, because that's when next we will be getting to the statistical test series of them. That's where we'll start. Pretty much the last bit of theory that we have to look at is these. Now we'll look at this, the types of error. That's what we'll be trying, like pretty much the last bit of test, like theory sort of thing. Then we'll start with the tests. Now let's have a look at what are these types of error. So we already know what is null and alternate. While we deal with data, we can make mistakes, we can make errors. What are those types of errors? So types of error is what we're trying to understand. What are the different types of error while we deal with data? So there are two types of error that we can come across. One is alpha error. This is also known as type 1 error. This is also known as manufacturer's risk. We'll look at what is the meaning of that, but let's have a look at other error. This is beta error. This is known as type 2 error. And this is also known as consumer's risk. What is the basic difference between these two types of error? And when do we end up making these errors? That's what we need to understand. Now, what is this type 1 error? Type 1 error is when we end up proving a null as alternate. We have committed a mistake. Yes, we have committed a mistake. If it was null, that means there was no relation, and we proved that there is a relation, that it's a root cause. We have made a mistake. What kind of mistake? It will be called as a type 1 error or alpha error. This situation is also called as innocent punished situation. Innocent punished situation. Well, somebody who is not a criminal, innocent person, because of wrong evidences, people giving wrong testimony, whatever, we end up fabricating the evidences, we try to influence the witnesses, we end up proving that the person has committed a crime. Well, that person is innocent. But if you end up proving it that no person is guilty, you've innocent gets punished. You have made a mistake. The court has made a mistake. The judge has made a mistake. That's when we have the court or judge has made a type 1 error or an alpha error. That's what we mean by this. On the contrary, the beta error is just opposite. When we end up proving alternate as null, something which was a root cause, really the impacting factor, root cause, we end up proving that no, it's not related. Well, then we have again made a mistake. What will this situation is called guilty released situation. So a lot of recruiters do ask this question: what kind of error have we committed if we end up proving something, somebody in an innocent, like we end up punishing an innocent? So yes, they try, you should know the synonyms. Accepting false null, yes, that's what, like, so bottom line, we try to kind of ensure that we should not get into these kind of situations, And the reason why we get into these null or alternate or alternate as null uh, is because of the mistakes we do in the measure phase. When would these errors come in picture? These errors will come because of two primary reasons. Again, the blunders we might have done in the measure phase. The reasons are sample size, insufficient sample size, can insufficient sample size. Basically, if you end up having insufficient sample, you'll be either a victim of a type 1 error or you'll be victim of type 2 error. So the people who traditionally who were not using the proper statistical methods, they were a victim of a type 1 or a type 2 error because you had lesser sample to deal with. And the inferences will be wrong. You might end up proving null as alternate as null. You have made a mistake. Second, say you have correct sample size or you have excess samples, which is good, but you messed up with the sampling methodology. The sampling methodology, you picked up a biased sample. You did not use the good sampling methodologies. When you had those bad sampling methodologies, those like your convenience sampling, quota sampling, judgment sampling, they were bad methods. And people used to like pay huge penalties because of that. Because people you were like there are instances in history where people have like taken decisions because of sampling methodologies and they were the bad ones. So you end up concluding incorrectly. Your interpretation is incorrect. So you will become a victim if you don't focus too much clearly. Yeah, election focus definitely yes, Gautam, without any doubt. In India, definitely yes, we have seen that blunders happening. It'll be sort of irrelevant to kind of go on to that like right now because yes, such a blunder happened in 2014 when Modi got elected for the first time. Such errors were committed and big time one, like pretty much it was a mockery of that forecasts. So yeah, so we can make such errors. This is and thanks to good methodologies we have today, we can like save ourselves from such embarrassments. So yes, using proper sampling like count and the methodology will be the right thing. We can go with the stratified random sampling when we're dealing with huge sampling method, or we can fuse them at our organization level. We can fuse the stratified random sampling with rational subgrouping to get a perfect sampling process, which will save us from any such errors, which is good. But we uh, saved from this particular error ever? No, we will always be at risk of these errors should you anyone messes around with these two things. That will bring you to this particular thing. Too early to like if you end up predicting or concluding too early too soon, you will be mm, like messing around with this process. So bottom line, if you don't do your basis correct, your measure phase is the base of your entire like analysis phase. So if your base is incorrect, your entire analysis will go wrong. So that's why it's very important that we must be very careful in the measure phase. Everything should be carefully done, planned, and like monitored, so we don't mess up with this. And that way there was so many checkpoints, the measurement system analysis and all that was there, just to be sure, because we don't want to end up in a situation where we kind of start working on something which is not a root cause, or we leave a real root cause saying no, it's not impacting, which will be a blunder. So I hope we're clear about this type 1 and type 2 errors. Is that okay with everyone? Okay, now perfect. Now let's get started with the test. So whenever you get a data like this, we are at stage where we have say completed the measure phase. You've done your sigma level calculation. What's your sigma level process. Now you've got the data ready. Now we want to start with your statistical test to find the root causes. That's what we want to do now. This data is available. What will be your first activity that you will do? So what are the sequence of events that will happen thereafter? So this is like the step-by-step sort of process, always how you should go about it. So hypothesis test is where we will start here. So that, let me just kind of edit this one, testing. Let me just keep it to hypothesis only. Otherwise, there'll be a repetition here. Okay. Now, first thing first, always, we will again start with normality, just to be sure that we have everything listed in a proper order. Whenever you get a data, I have no idea whether this is normal, non-normal. So first thing first, always go with normality testing. How do we do normality test? We use Anderson, Darling normality test. That's the first thing. Now, what is my, these are default definitions. What is my default definition with respect to normality, null and alternative? These are my default definitions. As per null, data is always normal. Standard, these are default definitions. Alternate will say no. Alternate will always have a problem. Alternate say no, data is non-normal. Now, how do we find whether data is normal or non-normal? Again, we'll test it. We have a data, we'll check this test, we'll do the test. What we will get is a p-value. Looking at p-value, we will understand is it null or alternate. And thumb rule, whenever we're testing this, whether null or alternate, basic fundamental is what we got to look at, p-value. So before we get in here, let's understand the concept of p-value, and then we'll kind of take it from here so that we understand the basic fundamental how normality, all these tests will happen. So first thing first, when we look at p-value, what is this p-value? Which will help us understand whether null is right or alternate is right. What is the basic meaning of p-value? P-value is the probability of making an incorrect judgment. It's not the probability of making a correct judgment or taking a correct decision. This is all about how wrong you can be. This is not about how right you can be. This is all about how wrong you can be. P-value. And probably the definition will get better, or understanding of p-value will get better when we look at a basic example. The concept will get clear. What is this p-value? So, but keep this in mind. This is all about how wrong you can be. Probability of making a wrong judgment. This is what it is. Now, let's have a quick look at this. Let me just get rid of this sheet and let me just copy paste this data. And let's have a look at this one. So we've got this data here. And so say, for example, when we did the normality test, and just stats, basic statistics, and then we go to graphical summary, say, we check this, see this particular data, the normality test, we get a p-value here. What does this p-value tell us? P-value is 0.587. That's what it says, 0.587. And when we did this test, if you look at, if you go back here, when we did this test, it says confidence level of 95%. That's what it means. It's confidence level of 95%. It says we're 95% confident about the predictions that we're making. Yeah, there can be a chance that we may be wrong, but the element of doubt is just 5%. We're 95% confident that whatever predictions we're making, that's correct. While there is 5% chance, yeah, you can be wrong. So going back to this, so all null definitions, standard null definitions come with your 95%. Everything that we do is 95% confidence level, which leaves us with 5% risk. This is known as alpha risk, which is this 0.05, which we just convert 5% this way. So you have an alpha risk. This risk is known as alpha risk. You have, with every null statement, you have this as fixed, standard. You don't, so this is there. You don't have a no debates around it. Like, so you're dealing with a 95% confidence, you're dealing with 1% risk. You have a probability that you can be wrong. What's the risk? 5%. Now, you come back and claim, no, null, you're wrong. You have a challenge here. You have a challenge coming from an alternate statement. You're trying to prove that no, null is wrong. Now, an alternate claim comes into picture, which claims that null is wrong. Now, when I'm claiming this, I have a risk of, so in alpha, like I have similarly, I have a risk of 0.08. Would you, this is fixed, right? This null's risk is fixed, 5%, because you're dealing with 95% confidence. What would you do? Like, you have a null definition which says there's no relation. And if you go with this definition, you have 5% chance that you will be wrong. If you go with this definition, you have 8% risk. Which one would you go with, null or alternate? If you go with null, which says there is no relation, you have 5% chance you may be wrong. But if you go with alternate, then there's 8% chance you will be wrong. You're trying to say, no, X has a relationship with Y. Would you go with null or would you go with alternate? We have 5% in risk in null and 8% risk in thanks. Always the lesser risk. Why would go with 8% risk when I know my null is only 5%? I will not go with 8% risk. There is no point in going with a higher risk. So I say we failed to reject null. We wanted to reject this null because of 5%, but unfortunately we have a bigger risk. Why would null get rejected here? Bottom line, that's what it is. We wanted to reject it, but we could not. Next, some other test we did. Again, we get a p-value, like this risk of alternate, we get a risk of 0.03. Now, which one would you go with? Null has 5%, which is not debatable, it's there. All we want to know, what is the risk of your alternate? Which one would you go with? Null or alternate? Alternate, yes, definitely yes. 5% risk is in null, 3% risk is in alternate. Why would I go with higher risk? No, well, you are bad this time. I have statistical evidence which confirms that there's a lesser risk. I will reject you and I will accept this alternate. I'll say we reject null and accept alternate. Simple as that. Because we have a better statement, a better definition, we have an evidence. It's not my gut feeling. We have an evidence which confirms there's a lesser risk than null. So we'll go with this. Definitely yes. What if I have 5% risk in alternate? Now, what would you do now? Null has 5%, alternate also has 5%. Would you go with null or would you go with alternate? You can't have both. Maybe situations no. Either it's null or alternate. Which one would you go with? Both has 5%. Null or alternate? Thanks, you all are right. Absolutely null. We failed to reject null. Well, you have 5% risk and I also have 5% risk. I am already proven. You are looking to be proved. Why I should change myself? I am already proven. You got to be better than me to reject me. You got to get better than me. So get me saying anything less than 5%, that's when I will get rejected. Bottom line, even if you're 5%, why should change? People believe me. This is all there, universal. You have to prove me wrong. When do you prove me wrong? When it's less than 5%. The bottom line, if you kind of summarize this, what is this risk are we talking about? This risk of alternate, because risk of null is already known to me. All I'm trying to find is what is the risk of alternate, and I'm taking a decision. What is this risk? This is nothing other than p-values. This all what we're getting is p-values. So when we get this p-values, so technically what we get is p-values nothing other than the risk of null, alternate, sorry. It helps you understand what is the risk of in going with alternate. Null you already know. So whenever you perform any statistical test, every test will give you a p-value. All what you do is compare with 0.05. Is it lesser than 5% or it's more than 5%? Basis that you take a decision. So yes, so if you want to kind of this, if you summarize this, if your p-value is less than 5%, if your p-value is less than 5%, then you reject null and accept alternate. Why? Because you have a lesser risk. Alternate risk, which is p-value, alternate risk is less than 5%. I will reject the null and I'll accept the alternate. What if we have a p-value which is equal or more than 5%? I will come to that just in a moment. If it's equal or more than 5%, then you failed to reject null. Same stuff. Just this is whatever we did here, we can try to summarize this. This is what we have to keep in mind every time. Whenever we are doing any statistical test, this is what we got to keep in mind, and we should get our answers. Now, Denzel, to answer your question, null, this is 5% is benchmark till the time you're working with 95% confidence. If your industry is working at 99% confidence, then your alpha risk is 1%. Depending on what is the level of confidence, your definition of risk will change. Then you will compare with, say, I'm dealing with the pharmaceutical industry or those kind of critical industries where I'm dealing with 99% confidence. Their 99% confidence leaves you 1% of alpha risk. Then this comparison will happen with 1%. I hope that's clear. But in general, thumb rule standard, it's 5% is for everyone, barring those industries. Okay, so this is how we find it. And like a lot of people, if you look at YouTube videos, and you generally find this, people generally using the slogan sort of thing to remember so that we don't get it wrong. If P is low, null must go. If P is high, null must fly. That's how different people use this sort of slogan to remember. If P is low, when P is low, null must go and alternate should come in. If P is high, null must fly. So null will continue. That's how people generally create this particular sort of slogan to remember it. So bottom line, in nutshell, whenever I'm looking at a p-value, all I'm trying to see is it less than 5% or not. If it's less, that's a validated root cause. You have been able to prove alternate. That means there is a root cause. It's a relationship there. So whenever we did do this testing, even say when we wanted to do the normality test, we did the test and null says data is normal, alternate says data is non-normal. We performed this test, normality test. Now, help me understand. This p-value says 0.587. So I'll just write it down. P-value. When we performed the test, we got a p-value of 0.587. Is this null or is this alternate? Would you go with null or would you go with alternate? P-value 0.587. You tested normality, you got a p-value of 0.587. Are you going to go with null or are you going to go with alternate? Null, thank you. Data, p-value when it's equal or more, that's null, definitely yes. If data is null, that means data is normal. This data is normal that I'm looking at. This data is normal. That's why this data is normal. P-value more than that. This data is normally distributed. Why? Because we have got the, if you look at this p-value, it falls into the zone, which is p-value is equal or more than. Yes, it is equal or more than. So that means null is proven, null is data is normal. That's how we find the data is normal or non-normal. So let's have a look at another example just to have a look at it. So that graphical summary. So I want to check it for CSAT score, customer satisfaction score. We perform this test, p-value less than 0.005. So p-value for this test, when I tested a different data, it is less than 0.005. What would you go with, null or alternate? Alternate, yes, because this is less. Alternate is proven. Alternate says data is non-normal. So the customer satisfactions data that I just picked up, customer CSAT score data, that is non-normally distributed. But when we checked the ticket closure time data, that was normally distributed. This data is non-normal. This data is normal. Bottom line, that's how it is, simple as that. So normality test is first what we do is normality test. Any data that comes in, we would like to know data is normal or not. Why? Because if data is normal, I look at mean of the data. If the data is not normal, I look at median of the data. That's my purpose. That's the reason I want to know whether it's normal or non-normal. So that's what I get to know after doing this test. Second activity, whenever I'm done with the normality, what's my second job? Second job is to find the randomness of the data. Now, what is this randomness? We'll look at that. We'll understand what's the meaning of randomness. But keep this in mind, a lot of recruiters do ask this question in a different way. Randomness, or people say it's stability. How do you check stability of the data? Stability, randomness, we're talking about the same thing. So keep this, I would use them as synonyms. So bottom line, that's what the same thing. Now, what is this randomness? We'll look at that, we'll understand that, but let's look at basic default definitions. Default, null and alternate. Same rule, same logic. Null, data is always random. Null always talks about good stuff. Null doesn't have a problem. So simple, data is non-random. So alternate has always a point to prove it's random or non-random. How do we check whether data is, again, a p-value? That's what we will get. What test do we perform here? Anderson Darling. Here the name of the test is run chart. Run chart is what we use for testing the randomness. We will, when we perform the test, we'll understand what is randomness. Let's perform the test first. Stat, you go to quality tools, and the first one is run chart. Stat, quality tools, and then run chart. We click on run chart. Ticket closure time is what I want to check. It's asking me for subgroup size. Subgroup, single subgroup, one data at a time, one data, single column. So my subgroup size is 1. That is all. I selected the data, selected the subgroup size, 1. Click OK. Now let me quickly show it to you. That's how your run chart looks like. And it will be very similar to control charts. When we study the control phase the last day, you'll see that this is almost a control chart. So when we'll get there, you'll understand it. They're very much correlated. The run chart and control chart, absolutely correlated. But let's understand where do we get the answer of randomness or stability. Look at this. There's p-value. P-value for clustering. There's a p-value here. P-value for mixture. This is some p-value. P-value for trend and p-value for oscillation. There are 4 p-values. We can see 4 p-values here. Now, what do they mean? Like, what do I do with this p-values? Not 1 p-value, 4 p-values. Let's understand. So we have different p-values to look at. So let's understand what is the meaning of randomness. That will help us understand. Any data which is free, so bottom line, let's free from any evident patterns is called random data. If data has no patterns, then it's a random data. There can be 4 different types of patterns, which is clustering, oscillation, mixture, and trend. These are 4 different patterns which can be present in a data. If none of these patterns, if it's free, any data which is free from the patterns will be random. Even if a single pattern is present in the data, it will make it non-random. Even if a single pattern is present. Bottom line, none of these patterns should be present in the data. If it's present, it's non-random. If they are not present, it's random. How do I know? Again, the p-value. If any p-value is less than 0.05, that means it will. So if any p-value, out of the 4 p-values is less than 0.05, it confirms the presence of that pattern. If any, so you have 4 p-values. If any single p-value is less than 0.05, that particular pattern is present in the data. That will confirm that this pattern is in the data, which is making it non-random. Let's have a look at the p-values again. P-value for clustering, not less than 0.05. P-value for mixture, not less than. P-value for trend, not less than. P-value for oscillation, it's not less than 0.05. This data is a random data because all p-values are more. None of these p-values are less than 0.05. This data is a random data. Let's have a look at another example so that we know how does a non-random data look like, so that we can differentiate between them. Let's quickly look at this. Let me change this to CSAT score. Well, that's a non-random data. Look at this. P-value for clustering less than 0.05. This has confirmed that there is a clustering issue in the data because it's less than 0.05. This is not. There is a trend issue in the data as well. So we have 2 patterns. Oscillation is also not there. So this data has become non-random because of clustering, because of trend. Both these patterns are present in the data, so which is making it non-random. Now, a basic question definitely should come to our mind. Why, like we know normal, non-normal, we know why did we do it, mean or median. what is the purpose of this randomness? What do I do with this? If I know it's random or if I know it's non-random, what am I going to do with that? Bottom line, there is a statistical test ANOVA which needs the data to be random. In case of non-random data, we will use non-parametric, which is not non-normal data test. We have to use, in case the data is non-random, then we'll use non-parametric test, Kruskal-Wallis. We'll just do that when we understand, but this is the purpose. When we start performing the test, we'll know when to use ANOVA, but it will come in picture. When we do this test ANOVA, before that, this is a prerequisite that whenever you're going to test ANOVA, the data must be random. If you know the data is non-random, you cannot do ANOVA. Instead of ANOVA, you will end up doing a Kruskal-Wallis test, which is a test for non-normal data. We'll be using that. So these are the two purposes of like basically randomness. Are we clear about this randomness part? Okay, perfect. Third thing is actually the test, hypothesis test. Now we start with the testing. So once we're done, these are the prerequisite. We've kind of understood the data types, like data stuff. Now we would start with the testing. Now, what are the different types of tests that we'll be dealing with? First thing first, you have a normal Y. That's what you have at the center here. In your spreadsheet, you will have X's. That's what you want to test, X on Y. You want to check whether it's a root cause or not. You will have numerical X's and you have categorical X's. Let's first have a look at them. You have some X's which are numerical, some X's which are categorical. When you copy paste this data on MINITAB, see, this data automatically is understood by MINITAB as a number or a text. This data remains C1 column, all numbers. This data had text, it becomes C2T. This data had text, C3T, alphanumeric, T, text, numbers only, C6, no T. So data is automatically understood by MINITAB as a number or a text. So some X's will be number, some X's will be categorical, which is text-based X's. Now, if you have numerical X, what is the name of the test you will be performing here? So the test you will be performing, so here the statistical test you will be performing and the graphical test. So you will have two types of tests. One is a statistical, another is a graphical. Statistical test will be correlation. This is the name of the test, and graphical test will be scatter plot. These two, this test will be done along with scatter plot, which will graphically will be represented by scatter plot to test whether X has a relationship with Y when your X is numerical X. When you're dealing with the categorical X, which is like text-based X's, here you will have two groups and 2 plus groups. Now, what is this 2 and 2 plus groups? That's what we need to understand. Before that, let's have a look at first 2 and 2 plus groups. What tests? I'll just write it down and then we'll understand it. 2 sample T test is when you're dealing with two groups, you'll be doing 2 sample T, and the graphical test will be box plot. We already done box plot. We know how to use box plot. This is one Way Anova, and again box plot. And here, in case of non-random Y, Kruskal-Wallis. If you have a non-random data, then you will, instead of ANOVA, you will do a Kruskal-Wallis. So these are the tests that you will be doing to understand which one of these are root causes. That's what we need to figure out. So let's have a quick look at these tests. Now, first thing first, let's understand what is two groups and what is 2 plus groups. Numerical X's, we all understand, say anything which is number-based X's. Let's have a look at the data first, understand the data. Okay, so that's the first one. That's my Y. numerical y. That's what I have. This is the first x where I am getting ticket handler. How many ticket handlers do we have here? 4, right? Jaya, Nitin, Ravi, and Vandana. 4 ticket handlers. So I have 4 groups here. I have data for Jaya, I have some data for Nitin, I have some data for Ravi, and some data for Vandana. So I have 4 groups, and I'm comparing them. I'm comparing the performance of different ticket handlers, how they have handled the IT ticket. So 4 groups, which will fall into 2 plus category, which where I will do ANOVA, because 2 plus will go with ANOVA. Let's have a look at this. Now, I have data for 2 groups only, male or female. So I'm comparing the male data versus female data. Well, 2 groups, 2 sample T test will be done for 2 groups. This is 2 plus. There are 3 groups, under 20, greater than 30, and between 20 and 30. So there are 3 groups which will fall into 2 plus category. Again, ANOVA will be done because it's more than 2 groups. In this case, ticket type, I have got 2 types of tickets, hardware issue, network issue, again 2 groups, 2 sample T test. This is all numbers, which will be all numerical X. Numerical X will be correlation test. So depending on the data type, we'll have to understand which test needs to be performed out of this list. Either if it's a 2 group, 2 sample T. If it's more than 2, ANOVA. If it's a numerical X, then a correlation test. I hope that's clear, and we can start with the testing. Everyone is okay with that? Okay. All right. So let's get started with the 2 sample T first. We'll start with 2 sample T ANOVA and then go back to correlation because there's something more to add in here. So 2 sample T is what we'll start with. So 2 sample T will be done on 2 groups, like male, female. What am I trying to do here? I'm trying to compare the average of male ticket closure time with the average of female ticket closure time. Null says male ticket closure time average and female ticket closure time average, they're same. Null says same. Alternate says no. They are different and they are significantly different. Let's find it out. Stat, basic statistics, and here we go down to 2 sample T. Stats, basic stats, and 2 sample T. We'll click on 2 sample T. Here, samples, we'll put our Y, and sample IDs will contain the X. So Y is my ticket closure time. So I put my ticket closure time here, and sample IDs, I put my X, which is gender of the ticket handler. It's 2 groups. So gender of the ticket handler is what I've selected here. That's it. We need to click OK. Job is done. Let's have a look at it. So 2 sample T test results. It tells me that there are, like, let's first of all look at the p-value first. What is this p-value? Like, is it null? Are you going to go with null or are you going to go with alternate? Null or alternate? Wenzel says alternate. How about others? P-value 0.00. Erwin says null. Alternate, Roman, okay. This is less than 0.05. It's alternate. When your p-value is less than 0.05, it is going to be alternate. If you look at this, p-value when less than 0.05, it's alternate. This is 0, it's less, so you have to go with alternate. P-value when it's less than 0.05 confirms that there is a relationship. Yes, this is a root cause. Gender is definitely a root cause. I'm not being gender biased. Well, we have an evidence here that yes, there is a significant difference between male and female. And we're not being gender biased, but there is one. There is a statistical difference, yes, and a significantly large difference between male and female performance. We're not being gender biased, but yes, there is a data backing up. That's what data is kind of giving us this clarity. Yes, there is a significant difference in their performance level. P-value, alternate, that's where we would like first to look at p-value to understand, is it a root cause? And that's the answer is available. Yes, it is a root cause. There is a significant difference in the performance level. Now I would like to understand which one is doing better or which one is doing worse. So females have 80 data points. Females have 80 data points in this sheet, and they have an average of 17.24. Male have 101 data points, and they have an average of 19.75 minutes. Time, lesser the better. This is ticket closure time, lesser the better. Females are doing a far better job. Now, few questions that we need to understand here and ask ourselves how to read and interpret this. We are looking at 80 data points for female. There's a 101 data points for male. That's a sample data. Well, you don't need to have a equal. That's not required. So if I have an average of first question, do I see a difference in the average performance? Yes, I do see a difference in the average performance. The female average is 17.24, male average is 19.75. Is this difference between this average, is it a large enough difference? Can I call this as a statistically significant difference? That's my first question. Second, what if I increase the sample? What if I reduce the sample? Will these averages still be same? Like it will look like a big difference? And what if I change the sample? What if I pick up a new sample? Will it still be a big difference? So the answer to all of those questions is yes. Looking at p-value, yes. The first answer is yes. Looking at p-value, I can confidently say that the difference we are seeing between male and female, these are statistically significant and large differences between male and female. So these are not small differences. These are not by chance. These are significant, real differences. And these are large differences, number one. Number two, from whichever process you have picked up this data, should you increase the sample? Should you reduce the sample? Should you pick up a new sample from this data? Forget about this sample, pick up a new sample from the process. You will still see this difference. It's not a matter of chance that you've got this difference. These differences are relatively large differences, and you will see them from the process. So whatever process you picked up this data from, in that process, you can safely conclude that the females have been doing and would be doing a better job as compared to male, and they would be significantly better than male. That's what we are able to interpret. A, are the differences large enough and real differences and not by chance? Number two, what if we change the sample? What if we increase it, reduce it, change the sample altogether and pick up a new sample from the process? We will still see these differences. So these are significantly large differences. That's how we need to read and interpret the two sample t-test, looking at the p-value. Let me do it once again for some other x, and let's understand how does it work out. Stats, basic stats, two sample t. So on the top goes my y's, and here it goes my x. So I've got my shift, I guess. Shift, we have got male, night, and morning sort of thing. I guess two shifts only. Let's see. Yes. Look at the p-value. Null or alternate? 0.922. Is it null or is it alternate? 0.922. Null. Thank you. Absolutely, yes. So the question is, do I see the morning shift average as 18.67, night shift average as 18.61? Well, I see a difference, but that's a small difference. Well, I can't safely say that this is a huge difference. And looking at the p-value, sorry, I don't get that confidence to say that, no, these differences are large. No, that's we do not have enough evidence to prove your claim. You had a claim, probably you had a claim that morning is better or night is better, whatever. You had a claim. Unfortunately, we do not have, looking at this data, we do not have enough evidence to support your claim. So we fail to reject the null hypothesis. Null hypothesis remains stands. So they are performing almost at the same level. There is no difference in the morning shift versus night shift performance. That's how we will read it. P-value, looking at p-value, we'll get our answers. Is it significantly large or it's not? Here, we do not have evidence to support the claim. So yes, null will stand true back again. So yes, that's how we look at the two sample t-test results. Is that okay with everyone? Okay, all right. So let's have a look at the other test, which is 2+ group, when we have more than two groups to deal with. When 2+ groups, we do one Way Anova test. Let's have a look at. So this ticket handling, like four different people involved in the ticket handling. Stats, ANOVA, one way. Stat, ANOVA, and one way. We click on this. Now response will contain my Y, and factor will contain my X, which is ticket handler. Now, ANOVA, we do an extra bit of testing here. We're just to get more clarity. We click on comparisons. And here we select Tuki. Tuki, I will see it's a very, very meaningful one because it brings more clarity to ANOVA. We'll look at that. So we selected Tuki, extra bit of clarity. Otherwise, we get a p-value still, but it helps better. Let's click OK. That's it. So we get some graphs, charts, whatever we look at. Bottom line, we'll be getting this data from here. So I'm just crossing it off for now. Let's have a look at this. This is what we want to know. Let's go back on the top. Null hypothesis. All means are equal. Null always says everyone is equal. Alternate says no. At least one mean is different. That's what alternate will always try to prove. Why no, they're not same. Significance value 5% is what we're working with. Have a look at this. Four groups that we'll be comparing. Have a look at p-value. Is this null or alternate? Are you going to go with null or are you going to go with alternate? Alternate. Yes, it's alternate. 0. P-value 0.00. It's alternate. Less than 0.05. Alternate. That's a root cause. Validated root cause. Yes, we have a ticket handler, which is a significantly like impacting factor. Yes. Now let's try to deep dive and understand which one. We got like four different people: Jaya, Nathan, Ravi, and Vandana. We know there is a sufficient statistical evidence which confirms that the performance levels are significantly different. Let's see who's good and who's bad. Let's just scroll down. Yeah, we'll have some evidence here, which we'll also look at Tuki, but let's understand it from here itself. Jaya has 22 data points in this sheet, 22 data points. She has an average of 19.9, 19, and that's an average for these 22 samples. But we're 95% confident that her ticket closure time will range between 17.7 till 20.6. That would be the ticket closure time range. She could go lowest up to 17.7 and maximum up to 20.6. That's for Jaya. Nitin has 56 samples in this data, which with an average of 20.6. And at the same rate, we can conclude that this is going to be the ticket closure time for Nitin to 19.7 till 21.5. In case of Ravi, you've got 45 values with an average of 18.66, and the ticket closure time will range between 17.6 till 19.69. Vandana has 58 samples with an average of 16.5. And her ticket closure time will range between 15.5 till 17.4. Look at her. She ends at 17.4. These guys don't even start at 17.4. This is 17.7, 19.7, 17.6. She ends at 17.4. That's where you're getting the root cause from. That's why you are seeing a significantly big difference. Why? Because she's a role model. She's delivering a performance which nobody else is close. She is absolutely phenomenal. Now, even if you don't have Vandana in this data, still you would have got an alternate. Why? Because Ravi is ending at 19.6 and Nitin is starting at 19.7. Absolutely different performance level. So 19.6 and 19.7. So he's starting at 19.7, he's ending at 19.6. No match. They're absolutely different levels. So his maximum is better than his minimum. So pretty much that's how it is. If we look at Tuki, it is a very easy way to understand what's good and what's bad. Have a look at this. It says means that do not share a letter are significantly different. Any group, like what they do is they give an alphabet to a group. So any group which has a different letter, that means they are significantly statistically different. Look at this. Nitin has been given an alphabet, like your data has a property of say A group. Jaya has similar features of A group, and she has some other features also, which has been termed as B. Ravi has a data of B, all data which is similar to B. So Jaya has something in common with both Nitin and Ravi, but Nitin and Ravi have nothing in common. So they are significantly statistically different, Ravi and Nitin. But look at Vandana, she's altogether different from everyone, league apart. So that's why I said, even if Vandana would not have been there, still we would have got alternate because of A and B. The moment you see any different alphabet, you have an alternate. Bottom line, in case of null, you'll all see as A. All will be A. That means everyone is same. The moment you see another alphabet, you know why you got an alternate. Who is the one who is different from the group. So let's have a look at another example. We'll be able to get more clarity here. ANOVA, one way. Remove the ticket handler. Say I want to compare different managers. I want to compare the performance. This is already selected. This Tuki one is already selected. Click OK. Just same stuff. Let's have a look at it. P value 0.364. Null. That's 0.364 is null. That means we do not have enough evidence to reject null. There are all the managers, we like 5 different managers performing at the same level. We do not have enough evidence to claim this manager is better than other one. Practically not. We don't have. Look at this performance. They're more like same. There's nothing in significantly different, bigger or smaller. And that's why you see Tuki, everything has been grouped under A. Whenever you see null, you'll always see Tuki as A. Whenever you see alternate, you'll always have a different alphabet. Is this okay with everyone? Anyone has a question about what we covered in the two sample T or ANOVA? Is that okay with everyone? Okay. Okay. Had this data been non-random, which we know the data is random, if this data would have been non-random, we would have done Kruskal-Wallis. Instead of ANOVA, we would have done a Kruskal-Wallis test. Now, where do we find the Kruskal-Wallis test is what we need to have a look at. So we know we will do run chart to find it's random or non-random. Let's have a look at it. Stats non-parametric. These are all non-normal tests. Kruskal-Wallis. Kruskal-Wallis is here. If your data is non-random, that's only when you select this non-normal test. Response is your Y, which is ticket closure time. Factor is your X, which is gender of the, say, not the gender, the ticket handler, 2+ group, ticket handler. It's a counterpart of your ANOVA, so 2+ group. So Kruskal-Wallis is the test for non-normal data, but only used here in case you have a non-random data. Have a look at this. It is comparing the median because non-normal data. It's testing non-normal stuff. It's comparing the medians, looking at p-value. It confirms yes, that's a root cause, and we have got a p-value which confirms that yes, there is a significant difference in the median performance of every ticket handler. So we see that Jaya has got lowest median, and we got the highest median of Nitin, and they are performing at absolutely different level. So yes, we know a root cause here. So if your data is non-random, instead of ANOVA, wherever you have to do ANOVA, you will be using this. Let's say we are trying to do a comparison at qualification level. We have got graduate, undergraduate, and postgraduate, 3 groups. And if my data is non-random, then I'll go with this one, say Kruskal-Wallis. Instead of ticket handler, I will use qualification. This is coming as null. We compare the medians. I can see a difference in the median, but is the difference large enough? Sorry. With the given data, we do not have enough evidence to support your claim. The differences could be there, yes, but these differences cannot be termed as significantly large differences. This could be just by a matter of chance. These cannot be termed as significantly large differences. That's how we would interpret this. Are we good with this? The Kruskal-Wallis, everyone? All right. So let's have a look at correlation test. Correlation is what we, yeah, correlation will have some bit of extra additional things that we will be looking at. Let me just get this other MINITAB in, because that's what I guess I've been using the older version because I prefer that. But I guess you all will be getting a MINITAB 19. That's what we should be. I should rather use this so that, because in correlation you get something which is different in older version. So that's what you will be having. So correlation test, before we do it, let's kind of quickly talk through this, because there is some bit of additional information you get in correlation other than what you get in p-value. So when you get perform any test, what you get is a p-value. P-value tells you if there is a relation or not. That's what it tells you. In this case, you get an R value also that you get a P value also, but you get an R value. What does this R value tells you? R value gives you two information. It tells you what is the nature of relationship between X and Y. And second, it tells you how strong is the relationship between X and Y. So these are two answers that I get by performing the correlation test. Now, what is the significance of this R value? R value will always range between -1 and +1. That will be the range of your R value. Every time whenever you're dealing with R value, you'll always see that this is the range of R value. Now, what do we further interpret from these ranges? Let's quickly understand this. If your R value ranges between 0 to 0.3, when your R value will be this is your, say, R value. Generally, what you'll have a P value here. What do we mean? This the meaning when you get zero to R value between 0 to 0.3, you generally get a null for this one. Generally, you'll have null. Generally, like practically every time when you have null, you'll see the R value like this. And what it means, there is negligible or no relation. When your R value ranges between 0.31 till 0.75, you'll say there is a weak or moderate relationship. And here you will always get an alternate. These are like sort of interlinked. When it's greater than 0.75, you'll say there's a strong relationship between X and Y. And you will also get an alternate for this one. Other than this is how strong is the relationship. This is what it tells you, how strong is the relationship between X and Y. Is it negligible or no relation, weak relationship, or strong relationship? It also tells you the nature of relationship. So nature of relationship basically means it comes with a positive, like, so it won't come with a positive means it will be a positive value, or it comes with a negative sign, like negative sign. Positive means if X increases, Y increases. That's directly proportional. Negative means if X increases, Y decreases. Inversely proportional. So let's have a small sort of example for this, and then we'll start with the test. What could be different values of this, and what could be various interpretations that we can make, say, from this one, say 0.87, and similarly we'll have, say, minus 0.27, minus 0.65, and similarly minus 0.91. What do we mean by this? This is positive, yes, but it falls into this zone, negligible or no relation. Well, similarly, we have this falls into similar zone, negligible or no relation. Here, it falls into the mid zone. So I'll say weak, positive relationship between X and Y. This is strong, positive relationship. This is weak negative relationship. This is strong negative relationship. That's how, when we look at R values, we'll be able to understand and interpret this particular function. So let's do the correlation test and let's figure out, like, so we have another sample data which we can look into the training material folder, which we definitely would recommend you all to kind of practice this. There's some bit of testing data capability test, and there's like it's hypothesis test we have. So there's some sample files for you to practice on to sample T Anova correlations, like some random test also. But yeah, this is what we're looking at: correlation and scatter plot. Correlation scatter plot is the test that we would like to see. What are the different types of data that we could come across with? So this kind of data, say sales and temperature, I'm kind of using this data to understand the, okay, let's have this then. Sales is my Y, my business problem. Temperature is my X, which is numerical X. So for numerical X, I will do a correlation test. I want to check whether temperature is correlated with sales. Does it impact sales? Null says no, no relation. Alternate says no. Temperature is a big driver of sales. It will impact sales. Let's do the correlation test. Sales stats, basic statistics, and we go down till correlation. Stats, basic stats, and correlation. I click on correlation. See, it doesn't matter. Normally, you have been seeing a different box for X, a different box for Y. Correlation, you get a single box. Ideally, what you should do is put X first and then the Y. So what is my X? My temperature. I want to check whether temperature will impact the sales. Temperature first, sales next. Go to results. In the results tab, select this pairwise correlation table. Pairwise correlation table, will you select this? Just click OK. That's what it'll give you. The graph, this graph, which is scatter plot. We'll talk about scatter plot also, but we just scroll down here. Let's have a look at this test results. What do you mean by this p-value? P-value 0.00. What does it tell you? Is there a relationship or not? Yes, it's there or not? P-value 0.00, null or alternate? There is a relationship, yes. It's alternate. It's alternate, yes, there is a relationship. Now, how strong is the relationship? What is the nature of relationship? This is R value, 0.953. What do you interpret out of that? Like, what meaning do you take out of that? 0.953. Thank you. Strong positive relationship? Absolutely yes. And that's what the graph also tells you. Let's have a look at the graph. Double click the graph, let it come up. Let it come up. Well, don't know why it's kind of used to work fine in my previous system, but it's yeah. It takes time somehow. Yeah. So here the same R value shows up, R value. And what we need to do is go to add item. Click on this and says regression fit. Click on regression fit here. It's chosen like linear. Just let it be there. Click OK. You'll see a line. This line tells you the nature of relationship and how strong is this relationship. When the X value was less, the temperature was less, the sales was less. As my temperature increased, my sales slowly, steadily increased. As my X increased, my temperature increased, my sales increased. My temperature increased, my sales increased. My temperature increased, my sales increased. The line going diagonally up gives you this indication, because without this line, it becomes sort of difficult for you to trace every data point and see where's the trend going. So when you have the line, it helps you understand this line is a regression line. We'll be learning about regression also, but for now, this line helps you to understand the trend. A line going diagonally up tells you there is a strong positive relationship. It's going up. X increases, Y increases. X low, Y low, X increase, X high, Y high. There's a strongly directly proportional. This is directly proportional. If x is less, y is less. X increases, y increases. That's what my R value also tells me. That's what my R value also tells me. So Pearson correlation coefficient of R value helps you to understand this. Let's check the other data. Let's let it come up. Okay, let's get the other data. What kind of different relationships we can see here? Uh, okay, that was positive. Let's have a look at age of the car and mileage of the car. So this is for like those industries who are dealing with second-hand car companies and all that. So they sell the stuff. Well, I would like to understand how my age of the car will impact the mileage of the car. Well, let's do a correlation test. Starts basic stats, and then we go to say correlation. First, age of the car, which is X. Second, mileage. X first, Y second. Results already, we have selected this pairwise correlation table. That's it. Let's click OK. And let's scroll down and have a look at this p-value. It confirms this is alternate. Yes, there is a relationship. But what kind of relationship we've got? Minus 0.967. Is this, what kind of relationship is this? Strong negative. Can the plot still tell us if the regression? No, this is all with relevance to the your linear model, not in terms of the quadratic nature. It's just the linear one. So when we're looking at this one, we are able to see there is a strong negative relationship between x and y, and we just scroll up. I can just have a look at this. Again, same process. Just we're trying to see what are the different kind of relationship we can kind of come across when we're dealing with this data set. You can have a strong positive, you can have a negative one also, like this one. A line going diagonally down confirms it's going down the drain. That's what it means. X is high, if the X is low, Y is high. X increases, it reduces the Y. If X increases, reduces the Y. It's inversely proportional. So X is low, Y is high. X increases, Y decreases. A line going diagonally down is negatively impacting the Y. So it has got negative relationship with it. And so that's what we see here. Uh, okay. So when you have the positive or negative, the line tells you the nature. So basically, all the data points are going down. So if you see the X is low, the age of the car was new, my mileage was high. As the car got older, my mileage reduced. The car got older, mileage reduced. The car got older, mileage reduced. So as my X is increasing, my Y is reducing. This line, which is going diagonally down, confirms that there's a negative relation. As the X increases, my Y reduces. So that's my negative correlation. When we talk about the previous one, which was positive, my line was going diagonally up as my X was increasing. So if I check this one, if my X was low, my Y was low. If my X increased, my Y increased. This is positive, strong positive relationship. We're going diagonally up. This is doing diagonally down, the other one. Is it clear, Ayush? Okay. We can have this kind of relationship also. So see, it's just different situations we can come across. So we're just trying to see what are different shapes we can see when we're kind of dealing with this. Stats, basic statistics, and then we go to correlation. I want to check whether number of hours I work, will it impact the salary? So I'm trying to understand the hours versus salary kind of range. Well, let's have a look at it. The image itself will be like self-explanatory. It's no, not strong. Well, in this data, it's not null, no relationship. It falls into the no relationship zone. Well, up to 0.3, no relation. And we look at the data itself, it tells you there doesn't seem to be a relationship. Well, it matters like whose salary are you looking at? Like, see, different people may be working like depending on what kind of nature of job somebody has, it varies too much. So probably it's just to kind of get a different kind of idea. We've got this data. Look at the data. It'll be flat line. Line helps you understand the trend of the data, almost a flat line. So if you look at it, say somebody is working, say like whatever this, some 60 some odd hours, say 63 hours is making 23,523. Somebody is working somewhat 90 hours is making 49,000, which is fine. You increase the hours, it increased, but it's around the same 90 hours, somebody is making 43,000. So there's 43,000 and 49,000, and then you around this, somebody's working 101 hours is making lesser. Well, doesn't seem to have, look at this. Somebody's working about 169 hours is making less money. So doesn't seem to have a relationship at the same level. So people are making less money, more money. For hours doesn't seem to be dictating or correlated with this thing. It doesn't matter whether you're working more, you're working less. You can see data has been all scattered. So there doesn't seem to be a relationship. Yes, probably yes. We kind of messed up different people's experts and junior workers salary structure. We kind of messed up everything together. But yeah, bottom line, the objective was to see to understand, like when you are trying to draw a relationship with any kind of organizational data, when you have an X and a Y. So similar, a lot of studies have been done. Like a lot of studies have been done. Like somebody wants to estimate, will the driving speed be correlated with number of accidents that are happening? Well, number of hours I study before the exam and the marks that I score in the exam. So there are different kind of studies people do, such studies just to understand if there is a correlation between them, and if it's what kind, if there is a relationship, what kind of relationship. You can get any kind of relationship, a positive, negative, no relation, strong, weak, everything is possible. So bottom line, these are different shapes that like we might come across when we deal with them. So correlation is some, this is how we end up dealing with correlation. Is everyone okay with the correlation part? Okay. All right. So pretty much the last topic that we have. So with this, actually, we conclude the analyze part, because this is all we need for testing all this data. So you already have the data with you. So I would definitely recommend you to try and test and explore about all these tests on MINITAB, and see which ones of the out of these are root causes, which ones are not. That's one. Other than this, there is some practice data. I would definitely recommend you to all to have a look at this. As I going back to data files for class, analyze folder, hypothesis test, and you have different files. Within these Excel files, the multiple files. So just try out these two sample T's, different tests, different samples. You have got different samples. Try them out. ANOVA, you have got different samples. You can look at them. So like, and this, once you're done with these two sample T ANOVA correlation, then pick up a random test file. This is a random test file. This is your Y, and these are your X's for you to practice. So you will be able to see. Uh, yeah, so root cause, yes, it will. So ones which have been proven as alternate are the real root causes. They will go through further root cause analysis in the improve phase to understand like why did it happen. If there is a problem, if it's a root cause, why is that? So the further drill down will happen on the x's, where we've got alternate. When p-value is less than 0.05, we try to do a deep dive into them. I hope that's clear, Renzo. P-value will confirm. Yeah. So do practice on this data. So like it's a, and finally, once you're done with this, then pick up the random test, because this has got like small twist in the data. So you will look at it, you will be able to understand. If you remember all the steps that we've kind of written down here, if you follow all the steps properly, you will not like starting from here, the normality and onwards. Keep that in mind when you're working on this random test. It has got like small twist in this data. So it'll be good practice for you to understand which test needs to be done, what will be the interpretation. It'll be a good thing to kind of work on. So with this being said, like practically we complete the analyze part. There's one more thing which we'll be covering up from improve phase, which is which we actually will be starting tomorrow. Like, but yes, one more testing, which is again linked with this test. We'll have some more test in improve phase also, but we will be covering up regression. So basic regression file. Let's understand what is regression, how do we deal with regression, and let's kind of like let's quickly have a look at it. So where is my file? Well, let me see. Okay, that's where we have the other file. Pardon me for, yeah, I have. Okay, so regression is this particular file we are trying to work on. Now let me first of all explain what this data is all about. When do we do regression? What is the purpose of regression? But like in the meantime, let me just go back to my MINITAB 17, which is what I prefer. Let me, okay, we're back to this. But before we go ahead, let me just explain what this data is. When do we use regression? And what is the purpose of this regression? Let's just kind of go ahead and understand that. So improve phase, when we are done with your finding the root causes, yeah, we understand which ones are the real ones, which are impacting the business problem. So we would first like to understand, like say, first thing, which one out of these root causes identified are most critical. I would like to understand which one is more important. See, I may get, say, 3 or 4 different root causes, but all root causes may not be equally important. Some may be very, very important, some may be less important. So I need to understand which ones are more important so I can focus more on them and lesser on like little on the other ones. So for that, we would be going ahead with the regression. Now, when we talk about regression, we'll be dealing with 2 types of regression. One is a simple regression, and another one is multiple regression. So simple regression will, we do 1x with y at a time. We get a p-value for every test that we do. We get r square and we get a linear equation. So these are different outputs of your simple regression. Multiple regression, we test multiple x's with y at the same time. We get p-values because they're multiple x's. We look at r square adjusted in case of multiple. What is that? We'll understand. And we get a linear equation here also. So we will be skipping this because it makes more sense to read it. It'll be repetition, but this is where it makes more sense to study the linear equation. Otherwise, like practically it'll be a duplicacy. So let's understand how do we go about it and what do we get when we do a regression here. So going back to this data, what is this data all about? Like here, say salary is my why, the business problem. This is again for some, say, HR firm, some recruitment team who's trying to come up with some sort of mathematical model to understand how can we offer the right salaries to the candidates. I don't want to offer salary basis my gut feeling, say X candidate comes in, we offer some salary, other person comes in, we offer some salary. Now we want to have some mathematical model which can help us with some reasoning as to what should be the right salary. So say people who are subject matter experts who have been into that industry, and they brainstorm and find out like what are the possible reasons which could be uh, influencing the salary. So somebody felt like male or female, whether you male or female, that could be a deciding factor in how much salary do you get. Well, somebody wants to say that the management is gender biased. Probably you are more favoring male, or somebody saying you're favoring females. Well, I don't want to be judgmental here. I would test myself. So we included this as a possible cause here for now. Some people felt, now, how well do you do during interview? Uh, that would definitely influence your salary. Well, so probably there we have a scoring mechanism, some sort of written exam, psychometric test, or some sort of test, we give the scoring on a scale of 1 to 10, we get some score. That would definitely impact. Well, that tells you how capable you are. You judged during the interviews. Well, we included that as a criteria also. Well, some people felt no, experience plays a very critical role, and that definitely influences the salary that you get. Well, we included that too. You can have more. For now, just to understand regression, we got this small sample data. Now we will be testing with the simple regression first. I'll just kind of get rid of this previous stuff. Okay, so we're starting with simple 1x with a y at a time. So, start regression and fit regression model. Start regression and fit regression model. I click on this. Now responses is where my y will come, continuous predictors where my numerical x's will come, and categorical predictors where my categorical, the text-based x's will come. So I will get my, so one x at a time is what we're doing. Salary is my y. Let's check with the numerical x's. So we have interview score and we've got years of experience. So let's use interview score. So impact of interview score on salary. Let's click OK. Get some values. Let's have a look at it. Okay, so it says regression for this interview score is the p-value confirms 0.00. That confirms there is a relationship between interview score and salary. Definitely, that's a factor which is impacting your the salary. This is related. But other than that, what we will be looking at is this R square. R square, it says 52.98%. 52.98. So let me just quickly make a note of this. Interview score. Interview score. 52.98. That's R square. I'm just gonna, this is R square. So, and the equation we're talking about, equation I'll skip as for a simple x. 1x we will get repeated later on. So 1x with y, p-value is what we've seen. We have got the R square. We looked at equation here. Let's do the testing with other x. Interview score replaced with experience. Would like to check that. Again, we have got a p-value for, which is confirming, yes, there is a relationship. P-value confirms the same. Let's have a look at R square. 83.26. 83.26 is R square. R square of experience here is 83.26. Well, let's read kind of again equation. I'm going to skip that for now. Equation I'm going to skip for now. So we're done with the numerical axis. Let's go ahead and check the categorical one, which is gender-based testing. Well, let's go back here. And so the gender ways, this is null. Null. We do not have evidence to reject null, and so there is no relationship here. We can't confirm that there is a gender-based relationship with salary. So there is no relation with respect to the gender, has no role to play in the salary decision. Let's look at R square, which is 10.06%. 10.06 is the R square. So I'll just put in the gender here as 10.06. So this was alternate, this was alternate, this was null. Now, what does this R square explains? What does it tell you? Looking at R square. So R square basically, it explains, so the degree of variability X causes, X explains in Y. How much of, so in a nutshell, in layman language, how much of impact X makes in Y, how much of the Y, the component of Y, like what degree or what percentage of Y is controlled or explained, like what's the, like if it X constitutes the Y, so the Y is a combination of a lot of factors. What percentage of Y is that X? In a simple layman's language, I would like to say like how much of impact will X make on Y is explained by this R square. Simple as that. Like this is my, it's in a, it like if we want to use the statistical way, like that's what I will say. The degree of variability, how much of impact or change in the y is explained by the x. So it tells you the influence factor of that x on y. Now, coming to multiple regression, let's have a look at multiple regression. So multiple regression, we test everything at a time here. So if you have a lot of x's, it's always advisable do it in batches of like 5 each at the max. Don't do too much, like you can do in batches. Otherwise, it becomes too clumsy to kind of deal with it. So I've tested both of, like we got just 3, so we test here. Now we will look at p-values. Interview score, alternate. Experience, alternate. Gender, null. No impact. There's no statistical evidence for us to kind of validate the same. So that's how we go about kind of confirming there's no relationship of this particular factor on your y. Uh, when we are dealing with this multiple regression, see, one thing we've got to keep in mind, when this interview is happening, if at all, like we know that interview is score is related, so the impact of interview is influencing its impact on the decision of salary. Experience is also influencing its impact on salary. Gender, if at all, if this 10.06%, if that is some impact, then also it is making some impact. So all these forces are acting on the y at the same time. These are not happening in silo. These are individual impact, what we have got. But these are not happening in silo. They're all happening at the same time. This is also impacting at the same time. This is also impacting at the same time. This one is also, if at all it has any impact. Some may be positively impacting with each other. Some may be canceling others' impact. The positive negative correlation is happening. What is my overall impact, the total impact, given all these forces? That is explained by R square adjusted. The overall adjusted after all these forces, like whatever, in the overall impact that I see on my y. That is explained by this one, which says R squared adjusted, which is 88.84. Given all these factors, the overall quality of the model, the effectiveness of the model is 88.84. Well, let's have a look at this value. 88.84 is the standard when I have all these factors in there. Now I would like to further understand how big is every factor, just to kind of understand this. Let's have a look at this. Let me do one thing, remove experience from this model. Just to test and see how big is this factor. You remove experience from this model. I just have interview score and gender. See how much impact does it make on your overall quality of the model. You go on top, look at this R square adjusted. It has tanked 55.74. So from 88 point something, whatever value it was, it has dropped down to 54.5.74. Let's add in here rather. Loss of experience. So if you remove experience from the model, it has dropped to 55.74. What is the drop in the overall quality of the model? 88.84 to 55.74. You have a significant drop of 33% in the quality of the model, which is a significant loss. So it's a big root cause in the entire model. Let's get in the experience back and remove the score. See how much do we lose because of score. The overall decisioning when it's happening on the salary, 82.43 is what we get down to. So loss of interview score is 82.43. Well, that is not a big drop the way we saw in experience. I'm not saying it's small, but it's relatively very small. 6.41%. It's not a small one, but no ways you can compare it. So experience is definitely a very big root cause and has a great deal of influence on the salary decision as compared with the interview score. Well, that's kind of what both of them are alternate. Let's bring in the interview score back again and remove the gender, which was the non-significant one, the null. Now we'll get the clean model. Technically, that's what we're waiting for. 88.78. Gender, loss of gender. Let's say loss of gender from the model. Well, 88.78, that's what we get down to. So we are better off getting rid of this null here. This is the overall role it was playing in your salary decision, if at all that makes sense. This was the only impact it was making, overall factor, which is negligible, nothing. So we've got a clean model here. We got all the both the factors which are alternate. Yes, that's what we would like to bring every time. So yeah, these are two root causes, validated root cause. We got a clean model. We know the overall effectiveness of the model. So these two factors explain 88.7% of the salary decision, the salary offer that we offer to the candidate. These explain, these two factors alone, these put together, they explain about 88.78%. So if you want to predict the salary, you can predict about 88.78% of the salary because of these two factors. Now we come to the equation that we've been kind of waiting for. Let's see if I can copy paste it. Okay, let's get back here. Let's see. Yep, this happens in 17 only. It doesn't happen in MINITAB 19. So that's why I prefer using 17. I can type in, doesn't, older features, older versions still give this. I can edit, I can type, but it doesn't help in, I mean, the latest version doesn't help. So it works as a notepad also. So anyways, what does it mean? So we got the equations like p values for everyone, r square we saw. This is what we wanted actually. In reality, we wanted to know how big is the root cause. Accordingly, we can devise a rational plan the strategies given the root causes, the impact. This is helping us with a mathematical model to create a calculator kind of thing, which will help us plan things. So this is based on an equation which is y is equal to c plus mx. Now let's quickly understand what does it mean, and like, so y is nothing other than your y is your salary here. So y is your salary, c is intercept in the language of your the statistics, but uh, in a layman language, this is minimum value of y in absence of x. Bottom line, when value of x is 0, value of y will be c. We'll look at that. M is, in the language of the statistics, it's slope, but in a simple layman language, it's a multiplier of x, and x is x. Simple. Let's try to interpret this using these values. What do we mean by this? So it says salary. Let's say put it salary here. It says it's 53.22, which is constant C. Then we have got plus 1.754. So I'll write it 1.754 multiplied 1.754 experience multiplied by experience. So this is what I'm going to keep it as blank. This is for experience factor. This is experience. And so these two will get multiplied. So 1.754 times experience, whatever is the experience, that's what it means. This is the value of experience. For 1.754 experience is 1.754 multiplied by experience will be this value. Similarly, it says 2.105 times interview score. So this is my interview score factor. And this is also getting multiplied. So 2.105 multiplied by interview score. Now, if you look at the equation, what it has, salary is equal to 53.22 plus whatever is the product of these two, which is this, plus whatever is the product of these two, which is this. That's what it means. Now, you've got a calculator created from the formula, from your own data, which is going to help you to predict the salary. Now, say there's somebody who comes for a job interview for recruitment purposes and is just out of college, has no experience, zero experience. Okay. So 1.754 multiplied by 0 still gives you 0. And scores 0 out of 10 in the interview. Scores 0. Nothing changed here also, because it will give me 0. So that's what's the minimum value of y in absence of x. When the x's are not present, this is the minimum value of y, constant value. When the value of x is 0, when the value of x is 0, value of y will be the constant value. Fixed minimum constant value, which is this, when your x's are not. So this is the bare minimum value of y, minimum value. Now, what if somebody else comes in, has 6.5 years of experience? So that 6.5 gets multiplied, you get this value, and scores 8 out of 10, offer the salary. You have it ready. Now, say somebody comes in with 10 years of experience and scores 3 out of 10, offer the salary. Simple as that. You got your calculator ready. You can use this calculator, but keep this in mind. One basic fundamental rule. You can only use this calculator. This calculator will only be effective till the time you are working within the ranges, keeping in mind, say you can come and say like, let me do this for somebody with the 40 years of experience. No, sorry. Did your data had 40 years in that? Like when you did this regression calculation, you never had experience. Let's see the maximum out of this. Now, this equation will hold true only till 21 years. Anything up to 21 years, you should be able to assess this, but nothing beyond that, because your equation, the model was not created for anything more than that. You can't try and test this for something like that, like which is going to be irrational. So you don't want to be using anything which is irrational. Yes, should you want to include that, then you should include that kind of data in the model to create an equation which can cover up for that range also. But using existing data for which this equation was not, like it has no such value when it was created, you can't use this. Is going to be wrong. So it will give you this is fine. 20 years is fine. It'll help you understand what should be the right salary that should be offered. So a lot of organizations have created different kind of calculators which works for them. People have used a salary calculator, attrition calculator, a lot of calculators, depending what's your need of the hour. And this is just the beginning of regression, because regression is a vast subject. But yeah, practically the base of it starts here. Yeah, any questions out here? Like I hope we're clear. Where do we find the value of m? This is coming from the equation. This is coming from the equation itself, Renzo. M is 1.754. This is m. M1, this is M2. No, this is coming from the data. As the data changes, this multiplier will also change. This is coming from the data. These are the variables which will be plugged in. The value of x's will be changed. This will be equation will be created. Yeah, absolutely. So the constant is the minimum wage. You must offer minimum. Anyone who steps in, you minimum salary that you'll end up offering is this. Rest, this is coming from your data. And this is also coming from your data, by the way. But yes, it's calculated from the data itself. Only thing which will vary thereafter will be this value of experience and will the value of the interview score. Any questions? Okay, I guess. So that is all for today. I guess we had rest. I would definitely recommend everyone to kind of just do a little bit of practice in case you get some time on the analyze part on the statistical test. You with your MINITAB, you already have the sample data. Just work on that. At least it will give you a fair bit of idea about that. That's what will bring the difference because it's important to get crystal clear idea about like which test needs to be done in what case. Rest doing it on MINITAB won't take time. Okay, I guess if there are no more questions, we can call it a day. In that case, anyone has any questions? Okay, then thanks everyone. Let's connect tomorrow, and good night and take care of yourself. Let's connect tomorrow then. Thank you. Thank you. Bye-bye.